from Lisa Everett on Quark and Lepton flavor physics. And then following this lecture, after a, I guess, half-hour break, is the final discussion session, which will be Kev and Ben. Yeah, and Ethan has posted the sorting algorithm in the Slack channel for that. So Lisa, please go ahead.
Okay, thank you very much, Heather, and thanks everybody for hanging in there on a Friday. So basically, the subject for today is to focus on the fermion mass puzzle of the Standard Model. So this is, of course, just the origin of the quark and lepton masses and the mixing angles. And just as I've been doing so far, first going to focus on the charged fermions, and we'll go to the neutrinos a little bit later. Okay, but let's first just sort of recall what the problem really is. Recall we have mass matrices M, U, D, E, and why not? Let's put the neutrino one in here right now as well. This was my notation for diagonalizing them. It's a common one, but one has to be careful because various conventions abound. Okay. So this would be some diagonal matrix MU and C and T. And similarly, we have the downs. And D and S and B. Here are our friends, the charged leptons. And finally, let's talk about the neutrinos. Okay, so neutrinos, if they're Dirac, we would have U nu L dagger M nu. U nu R would be the M nu diagonal. I'm just going to label those as M1, 2, 3. And if the neutrinos are Majorana, as we know, then the matrix structure is different. We have U nu L transpose M nu. I'll just write Majorana for this one. This is the Dirac. Okay. And U nu L is M nu diagonal. And of course, we had that the UCKM, which I'm now going to go back to my standard notation and just call it UCKM rather than B, UUL dagger, UDL, and then the neutrino, the lepton sector mixing is the PMNS matrix, which is UEL dagger, UUL in this notation. Okay. So the idea is, of course, to come up with a theory of these parameters. After all, the mass parameters and the mixing angles are, remember, they're obviously the masses for each of the sectors, and then the CKM has 4 parameters. The PMNS, if the neutrinos are Dirac, also has 4 parameters. There would be 2 extra Majorana phases if they're Majorana. This is, of course, always assuming 3 families only. Okay, nothing further, no sterols here. I'm just going to restrict myself in this lecture to that subject. Obviously, if conclusive evidence of a stereo neutrino was discovered, we would have to go back to the drawing board for the neutrino sector. Okay. So if you recall, we talked about the quark masses, as we well know. Basically, in each sector, right, the ups, the downs, the charged lepton for the leptons for the charged fermions, the mass spectrum is dominated by the mass of the 3rd family particle. So what this means in practice is that Mu, D, and E, we'll talk about neutrinos in a little bit, they basically are close to an interesting, let's call it a rank 1 limit. So let's imagine there's some coefficient, and we can always basically go to a basis, or at least a leading order. Essentially, there's only a 1 in the 3-3 entry, and everybody else is 0. Okay. Of course, that's not the only way that one can write down the rank 1 form, right, we can, instead of having just the 1 and the 3, 3, we could have a democratic mass matrix where there's all precisely ones in each of the entries of the 3 by 3. That's another way, because that's the thing that also has 2 0 mass eigenvalues. And so basically looking at these things in different bases is going to turn out to be part of the game. But the main thing to keep in mind is that this is basically the kind of structure that we're looking for. And you might assume that maybe this is some quote unquote symmetry limit, or at least there's some mechanism or dynamic such that third generation only acquires mass in some limiting procedure. We also know, of course, that these coefficients CU, DE are hierarchical themselves. CU generally is going to be much larger than CD and much larger than CE, okay? And that could come from Ucola couplings themselves. If there are multiple Higgs doublets, it could come from different Higgs webs as well, okay? So let's talk now about the splittings that are observed. And here we talked in detail about the actual numbers. Let's start making squiggle estimates. And the parameter I'm going to use to try to estimate them is our friend the Cabibbo angle. Lambda, which is basically, remember, the VUS, close to the VUS value of the CKM. Remember, this is the thing that's about 0.2, so in other words, about 1/10. Okay. And so one can look at various numerology, for example, mass ratios of the quarks. And if you do that, you see, roughly speaking, and these are squiggles, so they are rough, mu over mc is approximately mc over mt, which basically scales like lambda to the 4th power, so Cabibbo to the 4th, okay? And in the downs, we have md over s, ms, like ms over mb, and this is a smaller, sorry, it's a bigger number. This is reflecting the fact that the down type quarks have masses that aren't as split as the up type quarks, as we talked about, okay? And so we can look at those and say, okay, so one thing people have done when they first started looking at these ideas for fermion masses is to say, well, maybe because there's very large splittings in the up sector, maybe it's the downs that are the sort of dominant area, and we're going to see some of the first attempts sort of focus on the down quark sector in particular. Okay. Now for the leptons, charged leptons, you can play similar games. So for example, mu over m tau, again, approximately lambda squared. Me over mu is actually a teeny bit smaller, lambda cubed. We also have, among the charged fermions, things like the following: mv over m tau is approximately identity. They're not quite, as we know, but pretty close. Mb over mt is about Cabibbo cubed. Okay, so these are very hierarchical relations because this lambda is a very small parameter, as we know. It's about a 10th. Okay, it's a small number. Now, what about the neutrinos? Of course, there we don't know their mass scales. One sort of silly numerology you can do, and it's not obvious exactly how much one should take it seriously. Well, that's really true with all of these things, essentially, is to say, suppose we have our delta m squared, and let's just write it as solar over delta m squared atmospheric. And if you put in those numbers, okay, this thing basically is closer to order lambda than order lambda any higher power. Okay, so reflecting the fact that there's a weaker hierarchy basically in the neutrino sector generally. Okay, we don't exactly know, right? The details, as I'm sure we've heard about quite a bit this week, but we see that compared to the very strongly hierarchical charge fermions, we seem to have a slightly weaker one in the neutrino sector. Okay. So these are the things we're trying to understand. And what I wanted to do today was just to kind of give you a little bit of a sort of guide or a little tour through various first attempts at these types of problems. Okay, that means we're going to start with the quarks first, as done historically, and we'll turn later to some of the enormous amount of work that's been done in the neutrino sector. And the first thing people were trying to look at was to say, okay, we want to look for special forms for these mu and md, right? Now, special forms mean you have to specify everything in a particular basis. So whenever you're thinking about these special forms, you have to remember these are, once you pick a basis, you've been wondering, do my mass matrices, and for the charged fermions, that means do the associated Ucola coupling have a special form if I write them in a particular basis. And the idea is if they do, maybe they have, instead of having sort of a general arbitrary 3x3 complex form, maybe we have special forms such that you reduce the number of possible inputs and then try to over-constrain. Okay. So this was the sort of first set of ideas. Okay. So some of these special forms, you just sort of think about them phenomenologically, just sort of empirically. So you can just say, we want to over-constrain. In other words, reduce our input parameters. Because as we know, we can't, they're not all observable, right? We know already we can only observe a subset of the parameters in the Ucola sector because of the fact that we can't measure the right-handed rotations, and we can only measure a particular combination of the left-handed ones that appears in the charge current. So this type of approach led to a sort of general theme for, early theme for the quarks, which has largely persisted, which is maybe the mixing angles are functions of the mass ratios. The way I've written those squiggle estimates up above also kind of show as well. Remember, Cabibbo angle in the quark sector is one of the mixings. And in fact, one of the sort of successful relations of this sort is the following one, sine theta Cabibbo, which is again, basically our lambda parameter here, is equal to the square root of md over ms. Okay, so this is in a first sort of explored in a two-family context back in historically. In fact, this is a famous relation that has a name. It goes by the Gatto-Sartori-Tonin relation, or GST, or sometimes just Gatto relation. And this is from 1969. And this was sort of long before trying to find a full theory of all the masses. I just noticed empirically that this seemed to be a reasonable thing and ran with it. Okay. So the motivation then eventually is to try to, if we have certain special forms, to try to enforce them via some mechanism. So one mechanism could be via some symmetry. Okay. Maybe there's some unknown dynamics. Okay. Doing the same thing. Maybe we get things where we sort of have something at tree level is only allowed, and then we can generate corrections via loops or radiative generation of masses. Maybe they come from higher dimensional operators that are tree level. Okay. As I said, first we start with these special forms and eventually try to figure out how to implement them more consistently in a more complete theory. And as we'll see, there's some very nice ideas in this domain. And in general, for this problem, part of why the standard model fermion mass puzzle is such a tricky problem is that really the devil is in the details, as we will see. Okay. So I'd like to begin actually by turning your attention to a very nice paper of Steven Weinberg. Weinberg in 1977. So the paper is called The Problem of Mass. And I believe this was for some symposium in honor of Rabi. Rabi was famous for many things in physics. He was also famous for the quote, "Who ordered that?" about the muon, so it's especially relevant to think about generational masses in this context. But one of the things that's very nice about this paper, which I believe is just his sort of symposium talk write-up, is a quote. He starts out with a quote. It's a pretty long quote, but I'd like to read it because I think it sums up many aspects of our field very, very nicely, and I really recommend you guys. I'm not going to write it all out there on this lecture note because that's just going to take too much time, but I very much recommend, now that these early works are all scanned somewhere so they're pretty easily obtained by searching, to read what he first said. So here's how it begins. Weinberg writes, "I recently heard Rabi describe the early calculations of atomic spectra, which were carried out before the development of a systematic quantum mechanics, as being a blend of, quote, artistry and effrontery, end quote. Since those days, we have of course learned a great deal, and many things which were previously obscure now seem perfectly simple, while new obscurities have descended upon us. We have seen a satisfying synthesis of the theories of weak electromagnetic and strong interactions, which has provided explanations for many of the ad hoc hypotheses which had previously been introduced into particle physics on chiefly empirical grounds. However, one essential element of this systematic theory has remained obscure. We must take the masses of the leptons and quarks as input parameters without any real idea of where they came from. He then says, in this paper, to offer some observations on the determination of the quark masses and the problem of their origin. He says, as a discussion on the origin of the masses, I can only hope, in the spirit of Robbie's remark, that whatever these speculations lack in artistry, they will make up for in effrontery. So I like that combination, basically. Artistry and effrontery. I think we're going to see signs of both in a lot of the material I'm going to go over today. So what was Weinberg's set of ideas? So Weinberg was actually proposing a radiative mechanism. So basically, he was imagining that essentially there was a heavy generation. Remember, back in this times, it was basically just thinking about two families. And so imagine that basically you have one heavier family, and then the second, the lighter family gets masses generated via loops, which he thought would be due to gauge boson exchanges. In fact, his thought was that you can have things like ME over MU. Looks like MU over MC, roughly speaking, okay? Remember, they didn't exactly know MU very well back then. Goes like G squared over 4 pi, okay, times maybe some log factor, various ratio of masses that's not that big, okay, where G would be the weak coupling, okay? He would say naively in such a setup, we would also want MD over MS, okay, to be generated in this way, but the trouble was MD over MS is too large. So then he says, look, we need to have this thing already there at the tree level. So then he says, let's consider the following set of mass terms in your Lagrangian. So we're going to write minus A dl bar, and I'm going to put the gauge eigenstate labels here, SR0. Minus B SL bar d bar 0. Minus C SL bar 0 SR 0 plus the conjugate. Okay. His statement, which is perfectly correct, is you can always perform unitary transformations on your fields to eliminate the coupling DL0 bar DR0. So what we then have is a mass matrix that sort of looks familiar. And then he aims to diagonalize this matrix. And generally what will happen if you diagonalize such a matrix is that the mixing angle, which is the Cabibbo angle in this case, is just going to be some function of the ratios A over C and B over C, right? Because you could always pull a common factor C out. So the mixings are only going to be dependent on that ratio. Then he says, suppose, here's where we start making special structure assumptions. Suppose we have A equals B, absolute value. Then you can show that the theta C, the mixing angle, basically goes like the following, okay? MD over MS. So in other words, our friend the Gato relation. What one's done here to do this is to basically assume that A over C goes like theta Cabibbo and that A is much, much smaller than C. Okay. So others, including Wilczek and Z, followed up on these types of ideas, okay? And the first, however, I would say sort of definitive next step came by Frisch in 1979, who looked at 3 generations. And he had the same sort of idea. His idea was that the third generation, okay, the heavy one, is what we call the driving terms of the Quark mass matrices. So the B and the T are the dominant things. They're what comes in. That's the rank 1 limit once again. Then suppose the second generation, the S and the C, they rise as some first order in perturbation theory. And then the D and the U, the latest generation, as a second order perturbation. And he too was envisioning maybe some gauge boson type loops. Okay, so his ansatz for the form of the matrices, and this is what's known as the Frisch texture, is the following. So I'll write for the ups, and now I'm being lazy again about the notation. There really should be zeros on all these because we're not in the diagonal mass basis yet, but presumably you know what I mean. So we have 0A0 prime, 0B, 0B prime, C, and then here's the right-handed ones. Okay, plus the Hermitian conjugate, of course. And then we also have parallel structures for MU and MD. Okay, so in other words, then DL bar, SL bar, BL bar should be the same sort of form. Let's see if I can fit it on here. 0 A tilde 0, A tilde prime, 0 B tilde, and then we have B, oops, 0, 0 B tilde prime, C tilde prime, D right, S right, B right. Okay. So that was his ansatz, and the important feature was not only the presence of those zeros, but that the off-diagonal entries have equal magnitudes. Okay, so in other words, the 1, 2 entry and 2, 1 are the same. Okay. This is basically like saying we can go to a Hermitian basis. Okay, so that's what he claimed he was doing in any case. He wanted to go to a Hermitian basis, use the freedom in rephasings to sort of put yourself in a Hermitian form with these special assumptions. Okay, and then again, assume the hierarchy. You can imagine C and C tilde are supposed to be the dominant ones, whereas the B and B tilde are supposed to be the ones that come in at first order in perturbation theory, and the A and A tilde come in at second order. So therefore, we'd have generally A much less than B, absolute value much less than C, and the same for the tildes. Okay. His thinking was that maybe the B, for example, could go like G squared over 4 pi times C, etc. Okay. Then what you can do is you can solve for masses in this type of limit, right? C basically gives you the MT. E gives you essentially MT and C. And A is basically MU and C. Okay? And similarly for the downs. Remember, the top mass was certainly unknown then. Of course, they thought it was much, much smaller. Okay. But now what we can do is we can go further. We can calculate the Cabibbo angle. And you can obtain the relation. Okay, now instead of sort of squiggling it, I'm going to do a slightly better squiggle job. It basically looks like the following. Square root MD over MS minus e to the I5 MU over MC. Because remember, you have to calculate then the rotation angle in each sector and overlap them, right? And the phase is just some combination. Remember, we can have phases on those off-diagonal entries. I didn't specify them there. Only the magnitudes were set to be equal. So that was the prediction. And again, basically the thinking was that it gives you something close to the Gato relation, okay? MU over MC is a very small value, right? So even if you sort of try to use the phase angle part in there to boost it, it doesn't change it by that much. So it's a very successful prediction. Interestingly though, there's another prediction, which is for the CKM entry CB, And what you get is a similar type of relation. I'm squiggling it again. It goes like ms over mb minus e to the I phi, and this is some different combination of phases, mc over mt. Okay, C mass there. Okay, so this is the thing that at the time said, okay, look, maybe the top quark mass was in the range of anywhere between 40 and 60 GeV or so. If that's true, then this formula would be relatively successful for predicting the right size of VCB. Because remember, ms over mb ratio is similar to md over ms. But we know VCB is much smaller than, say, VCB, right? The 1,2 entry is bigger than the, this is the 2,3 entry, which goes like Cabilo squared. So what we need is a cancellation between these terms, and that means that the top quark mass can't be too big, otherwise you can't get the cancellation to happen. So this Frisch form is now excluded. It's been excluded for a long time due to this relation. Okay. Well, we can learn a few lessons from the Frisch form. Okay. One of the lessons, which turned out to be a sort of theme that kept on going throughout people's early exploration of the quarks and quark mass, theories of quark masses, and continues today, which is the idea of texture zeros. So if I scroll back up and stare at the Frisch ansatz, you see we have this, the form of the matrix is such that there's some zeros in certain places, and there's some sort of special looking features. So this became known as texture, meaning we have sort of parts of the matrix that have big entries, parts that have small entries, so it's got some sort of structure to it that people call it texture. And in particular, those zeros are important because generally if you fill in certain zeros, then you're not going to get the right hierarchy, okay, that you're looking for. So the general idea was you have these simplified structures where you have zeros in certain places. And again, you have to be a little careful in how you think about these things because, of course, we have to specify a basis when we write these things down. So what Frisch was generally doing was to say, I'm already specifying my basis in which I can take these things. Hermitian, I'm going to shuffle around the right-handed rotations to make that so. And then what I can do is I can always, essentially, often you can remove the 1, 3, and 3, 1. So notice this texture had the zeros here in the 1, 3, and the 3, 1 entries, okay? And basically, it can use that freedom, okay, we can use the freedom of the fact that the physics is going to be invariant under a common unitary transformation among mu and md. So if we take both quark masses, for example, and shift them.
Lisa, there's a couple of questions.
Sure, good, yes.
One is, can we not correct, I guess, the VCB relation by adding more parameters, I mean, to the top quark mass?
Yeah, so absolutely, the point is you'd have to, these Frisch textures are going to have to be modified generally. I think just adding it to the 3, 3 entry isn't going to do it. Basically, to fill in some of these zeros, okay? And the more you fill in the zeros, the more parameters generally you're going to have. So then you start losing this sort of, what people were originally first trying to do was sort of have actually predictive theories where you have fewer inputs than outputs. Okay, but yes, right. You can correct these, and this can be used as a starting point, and people have, in fact, tried to do exactly those things. Okay.
And then another question, can we associate discrete symmetries to these textures?
Yes, we can. And other symmetries as well. Yes, in general you can. And so the point is, in the beginning times, sort of looking for structures that can do the job, and then later on you can figure out how to generate them via symmetry or some other mechanism, but usually a symmetry. Yes, absolutely. Okay. So basically, one way, for example, just in relation to these questions, one of the first things you can try to do to change the bad VCB prediction of the original Frisch textures is actually fill in the 2, 2 entries for both of these things. Okay. If you do that, then what will turn out to happen is you can, roughly speaking, keep the successful Gato relation, but you can modify the VCB. Okay. So those are things you can do. Other things you can do is give up the parallel structures of the MU and MD. Okay, and people have explored all sorts of things, but as I'll get to in a minute, now that there's such a precision test of all the different CKM entries and the precise balances that you have to have, essentially what it turns out to happen is that you start having to reduce your number of these zeros, okay? So have more parameters in there. It's harder to get like the really nice, clean, super predictive things. It's very hard to get all these details right, okay? So Quark seems simple enough, okay, heavy third generation, light others, small mixings, but intricacy of the details is where many very simple structures actually kind of meet their maker, if you will, okay? So another famous paper quite a few years later is by Ramon, Roberts, and Ross, the triple R's, yeah, spell Roberts, right? And this is, I believe, 1994, okay? And so they have a nice paper called Stitching the Ucola Quilt, taking the textures theme to another level of metaphor. And this is a really nice paper if you sort of want to get a sense of various structures people are looking at and what can happen. So what they were looking at was theories in which they have 5 of these texture zeros. Okay. Original Frisch model has 6 because we're going to count each pair of off diagonals as 1. Okay. So they found at the time they basically gave up the parallel MU and MB. Okay. And they also were working with Hermitian structures. So they found at the time 5 allowed patterns. So one example of one of their allowed patterns was something like this. Basically, you know, actually, I won't bother to write it because it's basically what I just said. We're going to fill in. I think I'll indicate it here on the first one. Basically, for the ups, we're actually going to make it even more restrictive. Well, we're going to change it. We're going to fill in this entry, the 2, 2, and we're going to turn off the 2, 3s. And then for the downs, they're just put in a 2, 2 element. Okay, that's one case. So this is about sort of perturbing around these structures to see what can happen. Okay, and again, these are very predictive. But if you then look out in detail now at all of these different things, at least at the level in which they were modeled here, they're again ruled out by the precision data on the masses and the CKM entries. That being said, I highly recommend reading this paper, okay? And I remember this used to be a great struggle because you might know that the 1994 or 93 or so, where that was the beginning days of the archive. And so many times people would post their paper in the archive, and then if you try to click on it, it will say, you know, PDF cannot be generated or something, right? So many papers on the time, that's what happens. And so then you'd always want to read it, and then it wasn't there, and then you have to go to the library and take out the journal because that also wasn't online then either. And then often when you made the long, lonely trek usually to the library, you find that somebody stole that version of the bound journals because usually any one that you really want to read, some useful, interesting papers, you find that those journals somehow they're either not shelved or somebody was ever looking at them or somebody just took it away. So anyway, now you can see it. If you still go to the archive, I believe it still says it doesn't work, but now we can see the journal online relatively easily, and it's a very, very nice paper. So these types of ideas have continued, and in fact, there's even a very nice recent paper, so let's keep jumping. Okay, 2016, Yanagita and collaborator. Okay, and they call it Occam's razor. And so what they're looking for now is asymmetric structures, meaning instead of Hermitian type of objects, asymmetric, and they want in particular, they're going to work in a diagonal up quark mass basis for the up quarks. And then they want to place 3 zeros in the NB, okay, and see what you can do. And they find a number of possibilities that, as far as I know, are still allowed. Okay, and some turn out to be redundant. You know, that's another interesting sort of paper. Okay, but you get the idea. The idea is to sort of look for patterns that can work. Okay, and hopefully ones where you don't have, you know, many more input parameters than outputs. Okay, because that's what we're trying to go one step better. Okay, so then the next step is, how do you enforce such special structures? So clearly one of the main ways to think about it is to assume that there are symmetries. Okay. Okay. Another possibility, of course, is that there's some sort of dynamics that's forcing things to be something, right? So, for example, maybe in the context of a fully UV complete theory, we can understand dynamically why certain overlaps of wave functions are such that this is the structure that we have in the Ucola matrix. Okay, but in the basically in the, you know, setting of effective field theory, symmetries are sort of by far the most common sort of ways to explore how to enforce these structures, and there's generally two types. One of which being particularly important for this problem, and those are the ideas of the horizontal or family symmetries. Okay, and you can also have, perhaps in conjunction with the horizontal symmetry, you can have the vertical / gut symmetry. So horizontal and vertical, I guess, because we often write things like this: UCT DSB E mu tau mu E mu tau. Okay, didn't line them up very nicely, but you get the idea. So horizontal, we're going right across the different field, you know, the particles with the same charges. And then the vertical, of course, the gut is putting particles with different charges into broader multiplets because we've enlarged the standard model gauge group to a bigger group. Okay, and so often these types of problems have been explored in the gut symmetry context because it allows for a further reduction of parameters, at least a priori. We'll see that getting the details right, again, in the guts will turn out to lead to basically our hopes that the gut can connect various sectors and therefore reduce our number of inputs. Turns out to have its own issues, and we're going to have to put in new things again, and the parameters will proliferate again. Okay. And so if you have something in some symmetry limit, then maybe you can get corrections. You can either get them radiatively, as Weinberg was first thinking about, or you can get them via sort of, if it's some family symmetry breaking at a high scale, then there'd be suppressed non-normalizable operators that could exist even at tree level, etc. Okay. So that's the next sort of setup. And here, the paradigm usually goes by the name of Froggaard-Nielsen. Okay, and I believe this is also 1979. So the idea was to postulate a family with horizontal symmetry, GF, that distinguishes the generations. The GF is then spontaneously broken by a new set of fields that go by the name of flavons. Okay, so let me just collectively denote them as some phi, okay, like so. Okay, and maybe I'll call them phi sub A because I'm using I and J usually for family indices. Let's fix it. Okay, there we go. Okay, so some scale, I'm just going to call that lambda. And then the idea is you can then configure a parameter that one assumes to be small, which is going to be the ratio of the VEV of some phi field divided by the scale in which the symmetry is broken. So quite generally we have lambda is larger than the phi VEVs, which is generally much larger than the standard model Higgs VEV. Okay. So in other words, our epsilon parameter generally is quite small. Okay, so the idea is again that small numbers, here the small numbers are the fermion mass ratios and the fermion mixing angles of the quark sector, are given by ratios of mass scales. Okay, so how do we generate such things? Well, what Froggaard and Nielsen did is the following. They introduced new fields. Okay, let's call them Froggaard-Nielsen fields that couple in normalizable ways to the standard model and to the flavons. Now these flavons have to be heavy, right? If they're light, they're going to be around mediating flavor changing neutral currents like crazy, and so we really cannot have that, okay? But what we can do is we can imagine the following type of diagram. So this is the usual sort of setup. So let's suppose I have, on this side, I have a quark doublet, and on this side, I have the right-handed up, okay? And let's suppose I have some symmetry. So the prototype really is a U1, but it could be any symmetry you want. Let me just pick a U1. So the point is we have some U1 symmetry, and let's suppose my Q has a -3 charge under that symmetry, and my U has a 0 charge. Okay, so then that means, and I'm also going to take the Higgs to have 0 charge under this new U1, okay, this family symmetry. But then what we can have is our set of Froggaard-Nielsen fields, psi I, and these are just some, as I said, heavy fermions, okay? And suppose they couple like the following. You can have Q psi I phi. You can have psi I psi j phi, etc. Okay, like so. So then what we can do is we can put in an insertion. Here's the Higgs, okay, which is going to have a Bev eventually to give us our mass term. And then we can basically put in interactions. And remember, these phi's all get the Vevs, okay? So then we're going to go here. This is a Froggaard-Nielsen field inside this first element here that I'm pointing to. And then we have an interaction, then we have to go -2 because let's just say the phi one has a charge of 1, okay? And then we go to -1, and then finally we're there at 0. And so therefore we would have in this case, the epsilon is going to go like phi over lambda cubed. Okay, so that's where the lambda is basically the mass scale of the Froggaard-Nielsen fields. Okay, so that was their original picture. They call these things the spaghetti diagrams because it looks like pieces of spaghetti flying up there. Okay, if you're dealing with sort of more UV complete type of ideas, including string motivated objects or maybe granulified theories, then often you're going to have these higher dimensional operators generally there anyway, suppressed by some string scale or the gut scale. And you can have symmetries like this type of U1, the prototype being an anomalous U1, where you can actually calculate the value of the epsilon that you want, and you can have various pattern, the ratio be such that it's close to Cabibbo angle, etc. So people have explored these kinds of things. Let me just comment that many of these explorations are often done in the context of the supersymmetric theory. And the reason is very simple. First of all, as we've seen, generally the scale lambda, where the symmetry breaks, needs to be pretty high, okay? And so then whenever we have very high scales, you want to try to understand them in terms of naturalness and all that. So it's sort of natural to think of a case like supersymmetry where there isn't the gauge hierarchy problem there staring at you in the face with that fine tuning, okay? Also, maybe we're all just, people were excited about supersymmetry for many, many years / decades, including not only hierarchy problem, but also gauge coupling unification, or maybe we're all just stuck in a rut, but this often happens. But let me also comment that one advantage is actually that there's some control in supersymmetry over You have a little bit better theoretical control over the stability of these zeros in the Ucolas because, as we know, the superpotential generally is multiplicatively normalizable. So if you set the zero there, you're not going to sort of regenerate it, at least in the limit of exact supersymmetry. So this thing also has the advantage that you get some control of the texture zero. But I would say it's not required. Okay. So what should the G family then be? As I said, canonical example is U1, but there's many other possibilities. Remember we had U3 to the fifth here as the sort of global symmetry of the standard model that is only there if we switch up all the Ucola couplings of the up, down, and leptons. And so you might imagine that this thing is going to be some subgroup of this. Another option you can consider is that since the top quark Ucola coupling is order 1, okay, all right, it's Friday, I'm losing my ability to spell. Okay, then you often want the top quark Ucola coupling to come from a renormalizable operator, meaning you want it to be allowed at tree level by the symmetry. So then you can imagine that one you don't want to switch off to 0. So maybe instead I can write U3Q quark doublet cross U3U that we talked about before. If I keep MT on, that would be a U2Q cross U2U, and maybe that should be the sort of starting point and look for subgroups of that. Okay. And in fact, many models have been built based on, for example, a family symmetry based on U2. Okay, you can have abelian cases, you can have non-abelian cases, etc. There's all sorts of things you can do. Given what I just said here about the top, it's natural to imagine that whatever your family symmetry is, if it's non-abelian, maybe you'd want to have an embedding of your quarks in a 2+1, meaning rather than put all 3 families in some triplet representation, maybe you put the lighter 2 in a doublet and the third one in a singlet so that it's allowed by the symmetry. As I said, there's many examples of these types of things. As I said, a nice prototypical example is the U2 family symmetry, and Barbieri and collaborators have a nice set of papers on this from the 90s. Okay, where then there's a 2-stage breaking, basically, and you get kind of modified fresh type of structures that then can be kind of guaranteed by the symmetry, which is good. Okay.
Question.
Yes.
One of the students says, I was a bit confused by the spaghetti diagram. Do I understand correctly that the scalar vevs are absorbing the charges to give rise to a QU mass term?
No, what's happening is there's a coupling of the following type. There's a coupling between first of all, the first one over here is a coupling between, this one is the coupling between the Q, oh sorry, not that one, this one, the Q, the phi, and some Bogart-Nielsen field, okay? And so basically what's happening is you're having heavy fields in here which have different charges. So there's just this diagram that includes the phi. It's just when we go at the end of the day, we're looking for kind of a thing like the following, right? There's going to be some sort of blob. Here's Q and U, and then that's going to represent the mass. So all I'm doing is taking this whole sort of area here and saying that is represented by this. And you see, this is not a symmetry, but once we go through this set of interactions and replace things by their vevs, this is the effective operator we get.
So each propagator is going to give you a 1/λ, and each phi vev is going to give you, well, a phi vev
right. So
in the numerator.
The thing has that scaling, yes.
Okay. Another question, given that all of these models are very ad hoc, is there any consensus on generally preferred models or types of models?
No, I would say there is not. And I think that it's definitely true that many of these scenarios, there's a lot of kind of ingenious work out there. So when we describe them as saying there's no obvious, like that's the one, right? I don't think any of them are really like that. If anything really was, I think we'd all know about it. It's not for lack of trying. I'm just saying, as I said, in the end, the devil is really in the details. So I wanted to show you a little bit about the types of things people do and the types of issues that come up, okay? And there's a lot of them. And quarks have their set of issues, the leptons have their own set of issues, and then it's not so obvious to see how you meet them, or if you should meet them together in some framework where quarks and leptons might get masses from some physics that talks to both of them. Okay. So yes, I would say different people have their own preferences. Let me go to the next sort of set of things I was about to talk about, which was in the context of grand unified theories involving the vertical symmetry. And there, the idea, of course, is that you can then, let's just take SU5 as a canonical example. As we know, we can then put in, for example, a 5 bar, we can put in right-handed downs and the lepton doublet, and then a 10 is sort of the rest, Q-U-R-E-R, okay, and schematically, and then basically you can also then for the Higgs, basically a 5 Higgs, 5 bar Higgs pair, okay. That was sort of the standard thing to do, and you have Ucola coupling 10, 5, 5 bar Higgs, for example, and that gives you some connection between basically the YD and the YE in these types of theories, okay, because these ones not only have the YE, they also have the YD, so there's a relation, okay. And so very early on, however, it was realized that some of these naive relations in the vertical symmetry context are actually very problematic. So let me point you to, again, early kind of work on the guts by Georgi and Yarlskog. And they have their own texture. They sort of assume their own kind of UD structures, Frisch inspired, okay. I'm not going to write these things down in detail, except for to say MU, one like a Frisch. And the MD was a different sort of pattern. There was basically, let's see, I'll write it like so. There was basically sort of structures like this, and then there was a block here, and then this would be like a, 2, 2 is not 0. There would be like a e to the I phi, e to the minus I phi, so Hermitian, and then we're going to have a B in here, okay? And then the point was that for the E's, they should be the same, okay? But it turns out if they are the same, you get very, very bad relations, okay? Turns out what's actually needed is a -3 factor for the ME case. And this turns out to be generated if you add to your Higgs sector, instead of just having the 5, 5 bar, you have to add a 45 representation of SU5. And then the -3 comes out as some Clebsch-Gordon coefficient. So this Georgi-Yarlskog texture, and in particular that critical -3 factor that's needed for the ME, okay, has something that's persisted because it's related to the fact that they also put in, related to this sort of structure, is the fact that we have these things that are called Georgi-Yarlskog mass relations. Their specific model I just wrote down no longer works. It's, again, it gives you the wrong value for the VCV once again. But the main point they brought up was that essentially a down to charged lepton unification of Ucolas works okay for the third family, so MB equals M tau at some gut scale. Works reasonably well, but it's basically a disaster for the other 2 generations. What works better are the following relations. And those factors of 3 that come in are actually related to RG evolution and QCD factors because of having 3 quarks, okay? So basically, what they realized was that the sort of standard gut Ucola unification, as I said, it's okay for the third family. In models like SO10, where you also, there you put everybody into 16, so then you not only have MB equals M tau, you'd have MT equals MB equals M tau. Well, that looks pretty bad, but remember, this is at a high scale, and generally you're going to have different Higgs fields coupling MT and to give you the top quark. So if you're in a sort of large tan beta regime, that one can also reasonably work. Okay. So the basic idea is that this Ucola unification is okay for third generation, a disaster for the others, and it's going to then mean that the thing we wanted, which was the vertical symmetry to relate Ucolas, is going to have to be disrupted, and that's going to mean generally proliferating the Higgs representations to allow for proper generations of the masses. And so there's state-of-the-art work done on this. For example, SO10 context, all you have to do is look up. So basically current let's say SO10, I would say Stuart Robbie and his collaborators, they basically look at the full SO10, including all the, you know, things you need to generate proper quark masses and the gauge coupling running and everything, okay? And it's complicated and you actually have many parameters. Of course, since they're SO10, SO10 also has a right-hand neutrino, so they do that in the context of a type 1 seesaw model as well. So we'll get to that in a little bit. Okay. All right, so since I'm kind of spent a lot of time on the quarks already, I'd like to get to the leptons. Let me just comment, you know, there's several other sort of lines of reasoning one can look at, okay, to suppress the, right, we're trying to understand why we get suppressed masses for higher generation, for the lighter generations. So I already mentioned radiative mass generation. In fact, I guess Steven Weinberg just wrote another paper on this in 2020 that I haven't had a chance to read yet. But I guess when he writes a paper on fermion masses, it's so exciting that I think there's even a Popular Science article about it where people are like, wow, Weinberg's working on this again. So something to Google and check out what he's up to, okay? There's also this idea of sort of extra dimensions and localization, which I'm not gonna have time to cover. Another way, these are basically suppression mechanisms. There's also, in, for example, the context of string constructions, one can have exponentially suppressed Ucola. Basically, they go like e to the minus some, which is a over alpha prime, where alpha prime is the string tension. Okay, these are because in some cases you can show that these Ucolas are coming from instanton. Okay, for example, in brane worlds, when you have overlapping strings on intersecting branes, etc., you get these types of things. Okay. So that's sort of where I want to leave it for the quarks. Complicated and lots of details to worry about. So let's talk about the leptons. Okay. Okay. Where, as we know, we have more limited data right now, but we actually have a lot of data compared to where we were in the early 2000s. I mean, it's been fantastic what's happened, right? We know that there's a solar mixing angle that's pretty large, of order 33 plus degrees or so. There's the atmospheric one, which could be maximal or maybe a little bit more than maximal mixing. Okay, and then we have the reactor angle θ13 measured in 2012, which is of order 9 degrees or so, so closer to the Cabibbo size, where the other two are most certainly big. Okay, so very, very different structure. And so to then understand not only the charged lepton and neutrino masses and the PMNS parameters, right, we obviously have a much richer framework because of the fact that the neutrinos, basically they could be Dirac or they could be Majorana. I know Andre has already talked to you today about, for the Dirac case, right, then we have just another exacerbation of the suppression needed, right, because if everything just has to couple to the Higgs, then you wonder why all the masses aren't order 100 GeV, so the top quark only being, quote, natural in that context. So Dirac neutrinos mean you have to explain the very, very small Ucola couplings, order 10 to minus 12 or smaller. And so, of course, that doesn't mean there aren't examples. There are scenarios. But basically, you have to understand some extreme suppression in the Y news, okay? And furthermore, what I'd like to comment is that I think the Dirac case can be sort of most interesting in the context of, this is just a personal opinion rather than general fact, but in many theories beyond the standard model, there might be fields that look like right-handed neutrinos with respect to standard model quantum numbers, but they might have quantum numbers with respect to some new symmetries. If they do, then remember the sort of canonical type 1 seesaw involves them having some kind of bare right-handed Majorana neutrino mass matrix that's taken generally to be heavy. maybe you can't write that down, right? Because it's just new transpose. Maybe you can't write that down if the right neutrino is charged, okay? So if you have theories of that sort of, not a complete gauge singlet, in other words, standard model gauge singlet only, then the Dirac framework is a very interesting and useful one in that context, just to think about that. But I'm going to focus mainly here on the Majorana case. And of course, the prototype here is the type 1 seesaw. And more generally, just writing down the effective Weinberg operator. It's not the only thing you can do, as again, I know you know already, right? But by far, in terms of the exploration of the flavor mixing, by far, these are the most popular scenarios. It doesn't mean there's no work in the other contexts. It just means that there's by far the most here. So I'm going to take my time remaining and focus on these. Like so. And of course, the big excitement then is we see we have a very, very different pattern of the lepton mixing angles compared to the quarks. I often think that this is kind of the quote unquote hardest pattern, right? So we have these sort of two biggish angles, and we have a third one that's sort of largish like the Cabibbo angle, the biggest angle of the quark sector, right? It's not super small. So it could be that what we have is, this is a signifier that there's just not much structure, okay? For example, in the U nu L, the matrix that diagonalizes the neutrino mass matrix, and in particular, that's also kind of perhaps borne out a little bit as well from the fact that we know that the neutrino mass eigenvalues aren't as strongly hierarchical, so it's sort of more understandable to imagine sort of big mixing angles there. Okay, notice these are all kind of basis-dependent statements. Very often when people think about flavor mixing in the neutrino, the lepton sector, very often one starts out always setting the charged leptons to be diagonal and working in that basis. So all the big angles, everything is all coming from the neutrino sector. Of course, you can work in a different basis. The idea is to try to see if there's any clear pattern in a particular basis that might reveal where these structures are coming from. Okay. So large angles in the PMNS. Maybe there's anarchy there. And so perhaps the same kinds of games one plays with the quarks. You play for the charged leptons, but then you also have big mixing angles in the neutrino sector and not strongly hierarchical eigenvalues. And so that's a popular hypothesis that's been around for a while. I believe the first papers on this, I could be wrong about the details, but I think it's Hall et al. In 1999. And Andre has written many important papers on these on this topic, including some very impactful ones, both in 2003 and 2012, when the reactor angle is measured right up close to the bound. So it sort of means this hypothesis got some legs. Whereas if theta 1,3 was very, very small, it would be harder to imagine there's no structure whatsoever. Okay, so now this is one set of possibilities, and there's some work on this. I'd like to focus on the idea that these large mixings are signifiers of some structure. Okay, in the neutrino mixing matrix. Okay, so we're always going to be on some diagonal charged lepton. Okay. So if there's some structure, then the question is, well, what kind of structure actually is it? And the thing that's interesting is that the leptons are very different in character from the quarks. For the quarks, there's basically a unique starting point for the mixing, because the CKM basically is essentially identity up to small corrections. Okay, so you might imagine that there's some symmetry that says up and downs are diagonalized by the exact same matrix in some limit. Therefore, the CKM is identity, and then as we undergo the symmetry breaking, that's when we fill in the little details of the off-diagonal matrix. So maybe that's the sort of flavor expansion, etc., that perhaps is in the Cabibbo angle or some power of it, right? Whereas for the lepton mixing matrix, right, so if we write UCKM, is basically identity plus some order of Cabibbo, okay? If we try to write something similar for the PMNS matrix, then obviously the starting point, if this is some small correction, is certainly not the identity. In fact, what is it? We don't have a unique starting point. So we can imagine maybe there's some small parameter or maybe a set of parameters in the lepton sector that correct whatever the leading structure is. But whatever this thing is, it basically is going to have at least two big mixing angles. And it's certainly not unique. So that means there's many different theoretical starting points. Okay. And indeed, very often what people do, although you don't have to, this is just a model building choice, maybe it's lambda prime, maybe we can relate this to lambda or some power. Meaning the Cabibbo angle of the quark sector. Even if we don't know, we assume that those parameters are of that sort of size. It may not be exactly that same particular correction, but it could be. For example, in a context of some sort of quark-lepton unification, you might expect that if there are small effects going on in the quark sector that are Cabibbo, they might show up also in the lepton. Okay. And so this idea then is once we have these types of corrections, then whatever this W is, once we correct it, then whatever their mixing angles were in the W matrix in some sort of limiting case before we turn on the corrections are going to be corrected themselves. Okay. So this has been the sort of dominant paradigm for quite some time. And I think it was in part historical because of the fact that the smallest angle of theta 1,3 was, currently it's the one that's best measured by far now, but it was also the last one to be measured. So for a long time, there was a thought that maybe whatever this W is, maybe it's some function of a theta 1,2 nu, theta 2,3 nu, theta 1,3 nu, right? But suppose that thing is equal to 0, okay? So suppose, since that's the quote small one, we have two big ones there, and maybe the corrections, theta 1,3, go like your correction parameter. Okay? And in fact, this was something kind of explored early on just empirically. Again, remember, oftentimes in this business, you start with kind of empirical relations. So there was an empirical relation known as quark-lepton complementarity, where it was noticed that, hey, in the lepton sector, theta 2,3 minus theta 1,2 is close to the Cabibbo angle. And so that was sort of pointed out in 2004 as the data sort of became firmer. And then we're trying to figure out, is that some sort of principle that one can implement or can base models around? Okay. So one idea we can notice numerologically, theta 1,3 is very close numerically to Cabibbo angle over square root of 2. Okay, and this can turn out to happen very easily in a scenario in which suppose we start with this 1, 0 and this 1 pi over 4, and we have a UE L, which basically starts off as the identity, but then gets corrected, maybe in the same place as in the CKM in the 1, 2 sector. If that's true, then it turns out you can easily get this prediction just from the fact that the PMNS matrix is UEL dagger U. And this was pointed out long ago by Visiani and Ramon. He says 98, this one, he definitely was writing proceedings about this in 2004. Okay. But the thing I want to impart to you is that most model building attempts are basically to sort of say, okay, let's have this type of structure, and usually we do sort of fix the atmospheric one, the bare one, if you like, to be basically maximal. The reactor one initially to be 0, okay? And this one is going to be the thing that distinguishes different models. So if you like, oftentimes the useful figure of merit is sine squared theta 1, 2 nu. That's going to be the thing that distinguishes different scenarios. And in fact, tri-bimaximal mixing is the case where this parameter equals 1/3. Okay. And I don't know if we talked about tri-bimaximal mixing this morning, but this is a setup where the PMNS matrix actually takes this beautiful form where you have one column that's basically the maximal column where you have a 0, 1/√2, 1/√2, and then you have a trimaximal column where each entry is 1/√3. And then the other column, the first column, is just whatever the thing needs to be, unitary. Okay, so it's a beautiful structure. So this scenario has been explored a lot, and prior to the reactor angle measurement was thought, this is it, we've got to be onto something, because this thing actually looked good compared to some of the other things one comes up with. You're like, oh, look at that beautiful structure. But of course, once theta 1,3 is measured and not 0, tri-bimaximal mixing in its strict form is excluded by data, and it should serve instead as some bare structure in this sense that I have here, where we start off with something before we correct, and then we have to correct it. So a lot of model building attempts have been to start off with this structure and to correct it with various correction effects. But we can also have other possibilities, which I don't have time to write them all down. So bimaximal, for example, I'll just do one of them. That would be for the sine squared theta 1,2 mu is 1/2, and you can have various other ones. I myself have played around with ones which involve the golden mean, the golden ratio of, architecture and various aspects of the natural world. You can just play around with numerology. And then the key thing again is to say, can you get this from some sort of family symmetry? And the answer generally is yes, you can get this from discrete non-abelian family symmetries. In particular subgroups, SU3 or SO3. And so subgroups of rotation. So it started off being basically the Platonic solid type of subgroup. So rotations only by the tetrahedron, that gives you the A4 group, etc. Okay. So these are the types of things people explored. And I know I'm probably getting close to the end. Is that right, Heather? I'd like to sort of draw one more little figure, and one more little figure, and then I'm going to basically be stopping. Okay. So I want to just sort of show you then the typical structure for these models for the lepton sector. So, and this thematic is from Ping and Loon's review, which is a very nice review to look at for more details of this. So imagine you have some G family, okay? So this is some discrete group, and it's gonna have some generators, a set of them. So these finite groups have a finite number of entries, and they can be generated by, oftentimes one deals with ones which have 3 generators that are typically called S, T, and U. And the idea is the following. You then basically preserve different subgroups of GF in the charged lepton sector, okay, and neutrino sector. So why we have the large, so for example, these are going to be this is the T generator preserved for the charged leptons, the SU generators preserved for the neutrino sector. And so how this can happen is we have to introduce a set of flavons, I'm going to call them phi L for the charged lepton part, and a set of flavons phi nu for the neutrino sector. So they need to be 2 separate sectors that are somewhat sequestered from each other. So you break the group down to different subgroups in the 2 sectors. And the reason why different subgroups is important is because then what will happen is after you diagonalize the mass matrices, what's going to happen is that the PMNS matrix is going to be basically its structure completely dictated by the symmetry subgroups here in each of the 2 sectors. And since we know it involves large mixing angles, we don't want it to be the same subgroup, otherwise we get the identity matrix. So that's the structure. And in fact, generally, I'm almost done there, I promise. This is what we mean by saying a preserved subgroup. Yeah, that's going to be a T dagger. Let's put it like that. TME dagger T is equal to ME dagger. So this is the statement that the charged lepton mass matrix is invariant under T, because that's the preserved one in this breaking pattern. Okay. And similarly, maybe let's just look at the S one. S mu S is equal to M mu because we're in the Majorana. Okay. So what this means in practice is that we can take UEL dagger T UEL, and that's going to be some diagonal object. Okay. And U nu L dagger S U nu L is going to be equal to the diagonal S generator. So you see the preserved subgroups, which are generated by the generators that are preserved, right, completely dictate the structure of the matrices U nu L and UEL, and therefore the structure of the PM&S matrix independent of the mass eigenvalues. This is dictated by symmetries independent of the mass eigenvalues. And think about how different that is from the quarks. Okay. Quarks, we were relating mixing angles to mass ratios, okay, functions of them. Here we're saying, in this formalism, they're separated. Okay, so extremely different paradigm. Let me conclude by saying you can take this structure that I just drawn and you can add in CP violation. You can imagine that your theory has preserved CP, and then CP is spontaneously broken also by these sets of flavons that you generally have to add more to. Okay, so people have also done that because once the reactor angle was measured to be non-zero, it means that the Dirac phase of the PM&S matrix is physical, and that's going to be the next thing to try to get a handle on. And so there's a whole set of work on generalizing this to include CP. Okay, so there's enormous literature on that. And then there's enormous literature on trying to marry these two structures together. Okay. And the answer is that it's very, very difficult. So there's been a lot of work done. Simple structures seem to be very hard to identify. I think we are we've still, however, just scratched the surface. Shows the difficulty, the character of this problem. So there have been many interesting ideas explored. There are many new ideas needed. And with that, I'll stop there and just to say this is why this standard model fermion mass puzzle remains one of the biggest puzzles for physics beyond the standard model. All right, thank you. Thanks for giving me a little extra time too.
Thanks, Lisa. You're only 6 minutes over, which is
good. That's pretty good for
small,
me.
Small compared to the average. Here's a question. So in the stuff you just wrote, T generates a little group of the big group G, and
it's
then the question is,
yeah.
It's a subgroup. Okay, yeah. And so then the charged lepton flavors don't mix.
Oh no, it depends on the group, right? So I'm just saying what people are often doing is basically we know that the charged leptons, first of all, there are 3 separate masses, and we're working in the sort of generally one's trying to work in the diagonal charged lepton basis at leading order. Okay, so in essence, often people take this subgroup to be Z3 over here. Okay, and then the ones over here can just depend a lot on the different group you start with. Okay, it could be higher, right? So the point is, at leading order, we are having that the charged leptons aren't mixing. That's a typical sort of structure one has. That's the thing, the basis in which we're working. But what will happen is, because we have these flavon fields, etc., you see that what we're seeing is that it's not that we're getting a particular structure for what the PM&S matrix should be in the exact GF limit. If the family symmetry GF is exact, right, basically what will generally happen is that even at leading order, it doesn't give us really what we want. So let me just kind of scroll back to answer that question a little bit better. So when we talk about the quarks, if we're in some symmetry limit, our symmetry limit was sort of being the one that's going to give us this 1, okay? And then we have to break it, etc. Here, the sort of these discrete non-abelian symmetries are such that to sort of have them be fully imposed, then what happens is that essentially your mass matrices in both sectors usually are just very, very far from reality, okay? So what we need to do is actually to break it via this sort of first stage that I discussed here. This breaking here is just to give us that sort of general form of this W matrix, And then higher order corrections as well that come in, because then you're going to have higher order corrections from these flavon fields. Remember, we're working in a charged lepton diagonal mass basis. That's true at leading order only. We can then correct that. So generally, they're going to mix at leading at the next order, etc. So there's a lot of next level of complication that actually starts to happen. Yeah.
Okay, any other questions? People are a bit of time to chat. A follow-up on the charged lepton. So that can be tested on in Fermilab's mu to E experiments.
Well, remember that for most of these theories that we're dealing with here, what we're looking at is that the scale of the family symmetry breaking is generally exceedingly high. Okay, so all those flavons, et cetera, they're all at scales sort of far from where we can probe. Okay, so even at sort of precision level, we're not going to really be able to probe them. Reason why people typically take them high is to avoid the fact that the lower they go, the more likely you're going to run head on into the same sets of flavor constraints that I've been talking about in the past few days. Yeah. So I don't think you can't really test. This is the same thing. Eventually what this is giving you is it's going to give you some theory, which then, as long as we only have standard model particle content, right, can give you, will give you the standard model, which means we can only measure a subset of the parameters. And yes, you can get higher dimensional operators, but if they're going to be connected via the flavons, the suppression scale is very high.
So then I guess the only hope would be for parameters that aren't measured that precisely yet, if you can make a prediction and then have it borne out, as opposed to a post-diction, also known as a fit.
That's right. That's right. That's
yeah.
part of what one's hoping for. And I think also that might be also partly why oftentimes these things were kind of done in the context of supersymmetry, because then there was some hope was, look, supersymmetry has the right-hand fields, and then there's flavor mixing of the squarks, putting the right-hand.
Right, and then you can.
Yeah, but the problem is
you
that
probe it in the squark flavor.
Yeah, but of course the tricky thing there is that you actually have to be careful with such comments, because that presumes you know the supersymmetry breaking mechanism specifically, because it might have its own weird structure, right? Okay. So really you're only measuring some combination of things, but at the very least you'd have more observables, because you'd have the observability of the right-handed sector. Yeah.
Mm-hmm. I guess you would, I mean, it would be a function of the flavon scale, right? But you would presumably have predictions for some flavor violating stuff.
You should, but as I said, generally
you just get
standard to keep it up very high. Yeah. And especially in this context where we're sort of trying to make, put a lot of the work done in these sort of pictures here. When we talk about the neutrino sector, we're really talking about generating the Weinberg operator, right? Like so. So basically, we're wanting this to be at some, giving us this structure. So this is basically now the
right. That's true. That's like your 10 to the 15 G.
Basically, it's going to be even higher than that. Yeah, that's the traditional thing. It doesn't mean that's what has to be done. And probably one thing we should all try to do more carefully with these types of theories, and I think to some extent people are doing that some, with thinking about lepton flavor violation, is to see if we can bring certain things down. Remember, in the context of some other mechanisms for generating neutrino masses, for example, type 2 and type 3 seesaws, they have new fields that have electroweak quantum numbers, and in principle, there might be some better handle through them, etc. Yeah.
Okay. We should probably give the students a break before the discussion session. So the discussion session starts in 15 minutes. There's the 2 rooms, mu and E, and there's an algorithm for determining which room to go to in the Slack. And we'll have Kev and Ben in the discussions this afternoon. And so thanks a lot to Lisa for another nice lecture on some really kind of esoteric